Okay, this topic is Euler Integration, which is a numerical way of solving differential equations. What are differential equations? Well, we know a lot about algebraic equations, where you have an algebraic relationship, like the ideal gas law, PV equals nRT. We know how to deal with algebra to solve for one of the variables. So if we know all the values on the right-hand side, we can plug in values and solve for P. That's a nice algebraic relationship. Now, differential equations involve variables and derivatives of the variables. So in this case, we have a mass balance for something flowing in with a concentration, flowing out with a concentration, a reaction. Then we have an accumulation rate. Now the things we don't know, say if we know the value coming in, we don't know this concentration sub g, C sub g, and we don't know the derivative of C sub g. And C sub g is a function of time. So we have to not solve for the concentration, we can solve as the concentration as a function of time. We can use Euler integration for ordinary differential equations. An ordinary differential equation only depends on one variable, like time. A lot of times we talk about dynamic systems, things that change with time, so that's why we talk about that. But it doesn't have to be that. It could be like a temperature. You can solve differential equations for the temperature value inside a three-dimensional object. So temperature would become a function of x and y and z position at steady state. And if you include time, it could be a function of four variables. So your temperature in a block or whatever you're interested in could be a function of x, y, z, and t. And that's what ComSol will help us do later on in the semester. So if you know current values, for their simple ordinary differential equations, we only have one variable. So it depends only on position or time. We step forward and repeat. Now, an example of that may be if we have a simple differential equation, dy dt is a function of time. We approximate dy dt as delta y over delta t, and then we write out what delta y equals. It means y, one way of writing out delta y over delta t is y at t plus delta t minus y of t. If you solve this, rearrange it, you can end up with this nice little formula. Y at t plus delta t equals y at t plus delta t times the right-hand side. The right-hand side's over here. So if we know the right-hand side, and we know where y is right now, when we start out, we know what delta t is, and we know what the right-hand side of the differential equation is, we can solve for the next value of this differential equation at t plus delta t. So we're trying to find values of y. We're not just trying to find dy dt, we're trying to find y of t, which is not known. So we're trying to find a bunch of values for y of t. Ideally, we'd know the analytical solution, which would be a nice closed form like sine of x or sine of t or e to the minus t. But we don't always know that. We might just have a simulation that has to give us values for y of t at points, a numerical solution. Let's look at a graphical representation. So here we have this dy dt equals f of t. When we put this together, we know at some point in time we start off, and this is our value for y. At our initial point in time, say t1 is our starting point at time, we know dy dt, we know the value for y of t, and we know dy dt because we know the right-hand side of this equation. If we know the right-hand side and we know the value, we can move forward in time because we're going to approximate it as linear, and we move y of t from this value to this value. After delta t, because delta t times our right-hand side looks like a line. Basically, how far, this is like how far to the right we move, and this is the slope. The slope of our differential equation, or our solution to our differential equation, is right there. So our new value is going to be depending on this update equation. We know y of t, we know the right-hand side, we know delta t, we find the next value of y. We plug it into the function, we get the right-hand side at this point in time, we get the slope right there, and we do that again. We keep moving forward for approximate values for this true solution for y of t. Here, 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 here. The accuracy may not be very good. The true solution, if we had a true analytical solution, might be this red line, but we're getting approximate values at different points separated by delta t values. One way to improve that numerical integration accuracy is to make smaller approximate values. So we take smaller steps. Smaller delta t, we end up with having better accuracy, much closer to the true solution. Still off by a little bit, but the smaller steps you get, the better the solution is. The problem is it takes more work to get closer to the true solution. Let's consider a simple mass balance, going back to this glucose being consumed in a reactor. We have stuff flowing in, we have stuff flowing out, and there's a reaction basically getting rid of some of the glucose in this reactor. So it could be a bioreactor where there's fermentation going on. We have a flow in term, flow out, and a reaction term. We have an accumulation rate. If we actually have numbers for these values, so a 10-liter reactor, a flow rate of 1 liter per minute, a concentration of the glucose coming in, and a reaction rate value, 0.1. Now we can plug those into our differential equation to get numbers. We can rearrange the differential equation to get everything on the right-hand side and the derivative here on the left-hand side. Once we have these numbers, we realize the function ends up being this derivative on the left-hand side and the variable of interest on the right-hand side, and some constants. So this is our right-hand side, our f function of time, and this is our derivative. We've got to solve this starting at an initial value for the concentration. So we take our function and we realize it's just like the general form for the Euler integration. And starting at an initial value at time t equals 0, if we assume we're starting at 0, you don't have to start at 0, but in this case we're going to start at 0. We use this update equation with a delta t of 1. We're going to try and solve this by Euler integration. When we do that, your 0 iteration is starting at time 0, and we're going to step by delta t of 1 each point in time. So from 0 to 1 to 2 to 3 to 4. We start out, our initial value for y was 0. We plug these values into our function to get the right-hand side. So if we plug in 0 here, we're going to get 4 divided by 10, which is 0.4. So that's our f of t. And that f of t goes into the update equation here to get 0.4. So once you have the next value for y, you plug these guys in, you get 0.32 for the right-hand side of this equation. So you keep using this equation to figure out the right-hand side, and this equation to update to figure out the next value of y. So we figure out the right-hand side using these values. You keep going back and forth. Find the derivative, the right-hand side, the slope, and then use the slope, f of t. We know what delta t is fixed. We know where we are right now. We know where we are. We know what the slope is. We put these together to get the next value of y. You keep doing this repeatedly. So an analytical solution for this can be found because it's a simple linear differential equation. It's not too hard to solve this once you know what you're doing. The actual case is the concentration follows this profile. So we can evaluate this analytical solution at any point in time. And that's shown in the green line. So if we take that 2 minus 2 e to the minus 0.2t, it gives us this green solution. So at any point in time, we should be exactly on that line. The approximate solution was 0, these red lines for delta t equals 3. But you can see with delta t equals 1, it's a very close approximation. So if you take a big delta t, it sort of has the same trend, but the smaller values get very close to the true analytical solution. But it requires more work. You're doing 3 times as many function evaluations and 3 times as many steps. Now, how do we know that this is the analytical solution to our differential equation? So this is our differential equation. If we take the derivative of this, the derivative of this with respect to time is going to be negative 2 times negative 0.2 e to the, I got a derivative off there. Anyway, we take this value, this proposed function of time, and stick it into our differential equation. And when we do a little simplification, we end up getting this value, looks like this, which looks a lot like the derivative. So we can say that we've satisfied our differential equation. This solution satisfies this differential equation. And again, why are we doing this? There are cases where you may want to model an artificial pancreas or look at using an artificial pancreas for a dynamic patient model. And here's the system model involving some differential equations where the glucose and subcutaneous glucose and insulin values, these values all depend on time. There's other cases where we've looked at modeling in a metabolic pathway system where you take complex reaction pathways where you have things going on inside of the body, inside of a cell, and you write differential equations that relate how the concentrations affect each other. Or, again, a particulate process where you're looking at just simple particles flying around and hitting each other. To look at granulation, those velocity vectors, you can integrate them and figure out where the next position of your particle is if you know what the velocity is. So far we know 4 things. We know how to solve linear algebra, where we have linear equations, all the constants, constant times a variable, sets of these linear equations, put it in matrix vector form, find the matrix inverse. We can do Newton's method if we have a function we're trying to find out where f of x equals 0, or where g of x and h of x equal each other. We can use this update equation, Newton's formula, Newton's method, to find solutions to that nonlinear scalar equation. We can do trapezoidal integration. Given a function we want to integrate from a to b, we can use trapezoidal rule to approximate that integral without actually analytically solving the integral. And we can, given a differential equation, an ordinary differential equation, in this case it only depends on time, we can use an update equation to give us values for the solution of that differential equation that approximate that differential equation. That's basically what COMSOL does. It just does it on a much larger scale. That's all for today.